want to evaluate the integral from 0 to infinity of cosine x over x squared plus 1 dx. So first, this is an even integral, an even function, so I can rewrite it as half of the integral from minus infinity to infinity of cosine x over x squared plus 1, okay? Yes, because this is an even function here. Now I can say that this is the real part of e to the ix over x squared plus 1, okay? So I will have 1 over 2 times the real part of the integral from negative to positive infinity of e to the ix over x squared plus 1 dx. And then I will proceed as usual. I will find the poles. So x squared plus 1 is equal to 0, so x is equal to plus or minus I. Now I have an exponential here, so I need to find out which path is more appropriate, this path or the path along the upper half circle or the lower half circle. So we'll let x be equal to r e to the I theta. I will plug that x, so that r e to the I theta as an x inside this e to the ix. So we'll get e to the ir e to the I theta. Now I will use Euler's formula as usual, so instead of e to the I theta I will have cosine theta plus I sine theta. Now I will have e to the IR times cosine theta plus I sine theta. Now I will move the I inside, so I will get e to the r times I cosine theta minus sine theta, okay? Because we have an I squared here, we have this I here and this I here, so it's I squared, so negative 1. Now, if I want an exponential decay, that's the thing I'm looking for after all. So I know that my r will go toward positive infinity because it is a radius, so it cannot go toward a negative value. It will always be a positive number. So if r goes toward positive infinity, and that we already have a minus sign here, so a negative sign here, a sign of theta will need to be positive, okay? Because if it would be negative, we would have negative, negative, so positive, and so if r goes toward infinity, we would have e to g infinity, okay? And that would diverge, that's not what you want. And also, this I cosine theta here is bounded, okay? We have e to the I cosine theta, so we have e to the I something that is bounded by definition, okay? If you have e to the I something, that is by definition bounded, okay? Because this is a circle after all. Yeah, I hope that this is clear. So sine of theta needs to be positive, and that means for if sine theta is positive, if we take the path along the upper half circle. Okay, so in the upper half plane. So again, I will split my path into two parts. I will go counterclockwise. Okay, so I will start here at negative infinity. I will go to positive infinity. I will go like that. Okay, I will split it into two parts. And now I'm going to prove that the second part, the part along the upper half circle, vanishes as r gets larger and larger. So we'll have x is equal to r e to the pi I t. T is between 0 and 1. dx is equal to pi I r e to the pi I t dt. And so I will replace everything with every x and dx with t and dt. So we'll have the integral from 0 to 1 of e to the I r e pi I t, okay? This e to the I r e pi I t, it's this original e to the ix, but now x is r e to the pi I t over 1 plus r squared e to the 2 pi I t times pi I r e to the pi I t dt, okay? This is my dx, and this is my x squared, okay? Now I will focus on this e to the I r e to the pi I t. So I will use again Euler's formula and put the I here inside. So we have I cosine pi t minus sine pi t. Okay, and again, because there's an I here and there's an I inside Euler's formula, so we'll have I squared here. Okay, that is an I squared. An I squared, yes. So now again, if my radius goes toward infinity, and also we know that sine of pi t is positive, first because it is positive in the upper half plane, and secondly because it is also positive, sine of pi t is positive if t is between 0 and 1, okay, if we take t is equal to a half, we will have, for example, sinus of pi over 2, so it will be 1. Okay, if t would be between 0 and negative 1, sin of pi t would be negative. For example, sinus of negative pi over 2 would be negative 1, but that's not the case here, so we don't care about it. Okay, so sin of pi t is positive. Remember that e to the I cosine pi t, as said before, is bounded, so we don't care about this part here. We know that r is a positive number, we have a negative sign here, a positive number here, so we will get our negative times positive, so negative, so we will have our e to the minus infinity, which will tend toward 0, okay? So our infinity is r as usual, and our negative sign is here, and sin of pi t is positive, so it doesn't change anything. So that will go to 0, and we would be done, okay? So we now proved again that the second part vanishes, and now we use the residue theorem. We know that the contour integral along this path, which is it is made of parts 1 and 2. So 1 is the part along the real axis, which is our original integral, okay, because it's from negative infinity to positive infinity, okay, plus our second path, which vanishes as said. So it will be our original integral plus 0 is equal to 2 pi I times the sum of the residue. Again here 2 pi I, it is positive because we are going in a counterclockwise direction. If it would be if it would be clockwise, it would be negative, but here it's counterclockwise, so it's positive, okay? And the sum of our residues, we only have one residue inside our domain. It is for x is equal to positive I, okay, negative I would be the lower half plane, that's not the case, okay? And so here it is a pole of order 1, okay, because we have nothing squared in the denominator. Not the whole denominator is not squared to the third power or whatever it is to the first power. So we can use the residue formula for poles of order 1. That is that everything above the fraction bar it stays the same, and everything below it we just take the derivative of it, okay? So we will have e to the ix, okay? So the same as here, and below we will take the derivative of x squared plus 1, so that will be 2x, okay? So 1 is a constant. Now we plug in x is equal to I, which is our only pole inside our domain, as said. Negative I is not inside, and so we will have e to the I squared, so e to the minus 1 over 2I, okay? So 2 times I. And so now we multiply by 2 pi I, the 2 and the I here cancel each other, we are left with p times e to the negative I, okay? And so now to find the original integral, we know that it is half times the real part of this result here. So we take half times the real part of this here, okay? And so the real part of that is the same thing because there is no imaginary part, and then we take half of it, so we're left with pi times e to the negative 1 over 2, okay? And that is our final result. So again, same procedure. First, we can see here that it is an even function, so we can say that if it goes from 0 to infinity, we can say that it is half the thing from negative to positive infinity. Now we say that this cosine of x, it is in the denominator, so above the fraction bar, so that can be written as the real part of e to the ix, okay? In the last video we had cosine of sx, that is the real part of e to the isx, okay, because we have the coefficient s in front of the x, but it doesn't change anything. So next we find the poles, so we set the denominator equal to 0, we find x is equal to plus minus I, then we find out which path is suitable, is more appropriate for our integral, okay? And we found out that to get the exponential decay, we need to go along the upper half circle and not the lower half one, okay? And then again we prove that this part along the upper half circle vanishes and that we're only left with the part along the real axis. And then we use our residue theorem, and we said that integral plus 0, so that first and second part equal to 2 pi I times the sum of the residues. Again, the 0 is because the second part vanishes, as proven here. and we only left with the first part, which is our original integral, okay? Because it goes from negative to positive infinity, okay? Yes. So this thing here, I mean, this original integral here, I mean. Yes, so then we find the residues with a pole of order 1, so it's a lot easier than if it were of order 2 or greater. So we just take the derivative in the denominator, and then we plug in our poles. When you have one pole, x is equal to I, because x is equal to negative I is outside. And so if you plug that I inside, here we get this result here, so e to the minus 1 over 2i. Now we multiply by 2 pi I, like here, and we get pi e to the minus 1. And now we know that to get our original integral, we need to take the real part of it. That's the same thing, because there is no imaginary part, and then we divide by 2, okay? Yes, because because this at the beginning we thought that this goes from 0 to infinity, but it is an even function, so we said that it is half the same thing from negative to positive infinity, okay? And so at the end you will have to that pi times e to the minus 1 over 2, okay? And that is our final result. Okay, so yeah, thanks for watching. I hope it was clear. Yes, thank you.